All right, welcome to this video. This video is the mathematics of economics. So this is really more of an appendix, a brief look into what sort of mathematics you're going to need when focusing on this class. So the first one is that economists rely very heavily on graphs. So we use graphs quite a bit to teach us or to understand what's going on. And we use different graphs for different reasons. So we think of graphs like maps. So a graph is really a simplified version of reality. So we build a simple model, and then we build a graph based on that model, and we want to understand what happens in that graph in certain situations. Okay? In no way are we saying that's reality. So for example, if you want to get around New York City, you would maybe look at a street map or a subway map, right? But that's a simplified version of New York City. No one would ever confuse a map of New York City for New York City itself, right? New York City is a very, very, very complex thing. So they want to know what restaurants are where, how many stories is this building, how many people are in this building, how many bathrooms are in this building, how tall are the buildings, how deep below ground do they go, where are the water systems in New York City, where are the electrical lines in New York City, where is everybody at every single moment. New York is a very, very confusing place, right? However, if you want to know how do I get from point A to point B, you'd want to wipe away everything about New York City except the layout and how you can best get from point A to point B. If you're taking the subway, you'd want a subway map, okay? If you're going to be driving, you would probably want a street map, right? And so we take a simplified version of New York City, and that gets us to what we want. But different types of maps, or in economics, different types of graphs give us different types of outcomes because we're focusing on what we want to learn. Okay. So another example would be if I want to go to Colorado and I need to know how to get to Colorado, a street map or a highway map would be a good way to show me how I can get from Des Moines, Iowa to Denver, Colorado. However, if I want to go hiking out in the wilderness in Denver, Colorado, street map probably wouldn't help me very much. I know that I'm somewhere in this green area like a national forest. Okay. However, a topographical map of Colorado would help me when I'm hiking. So again, I have a different need for a different kind of map because of a different situation. So when we focus on graphs, we have different types of graphs to help us understand what's going on. So let's look at a couple of ways that we can use graphs and a couple of graphs that we use. Okay. So we have, the first type of graph is a one variable graph. And a variable is just something that can be changed. Okay, so we have one variable graphs. And there's a few different types. So the first one may be a bar graph. The second type of graph that we might use may be a pie chart. And the third type might be like a time series or a line graph. Okay, so we might use a bar graph in the case of, suppose we have two countries over 2 years and we want to understand the differences. So number of hours studying economics. So this would be a bar graph. Okay, so here we have the number of hours studying econ. Okay, and we have two different countries. So the first country, let me grab a different colored pen here. All right, so the first one, we might use the US, and the US will be in red. So this is going to be for 2007, and then we'll look at 2012. Okay, so we have 2007 and 2012, and we're studying two countries, the US and let's say France. Okay, so for the US, people on average studied 5 hours a week, let's say. So we might have one bar. And then we have a little box that says our legend that tells us red is the US. And then in 2012, people studying on average 3 hours a week in the US. Okay. And then our second one, our green, is going to be France. Okay, so let's say people on average in France spent 6 hours a week studying in 2007. And in 2012, they spent on average 5 hours a week. Okay, that will be a good use of a bar graph. So we have one variable, number of hours studying economics, and we have a few different countries, and we're comparing how they change over time, or we're comparing two different countries. Or I might use a bar graph, and I have a different color for each different country. Okay, so it might be 1 year for 10 countries, and we have 10 different bars for each country. So a bar graph is a good way to view this type of data. Okay, the second type is a pie chart. Okay, now suppose that we have some raw data. Suppose that I want to understand how you spend your day. Okay. Or let's say you have 100 hours and I have you track yourself for 100 hours. And I categorize it into 4 things. So you have working out, sleeping, studying, and leisure. Okay, so you have those 4 things, and I'm having you track what you do for 100 continuous hours. So let's say in this 100 hours, you spend 7 hours working out. You spend 20 hours sleeping. You spend 40 hours studying. And then that means that you spent 33 hours on leisurely activities, such as hanging out with friends, watching TV, eating, and so forth. Okay? So you have 100 hours, and a bar or a pie chart would best represent the breakdown of your time. So here we would have 4 different boxes again, 4 different colors. And this will be working out. Blue will be sleeping. Green would be studying. And we'll call red fun or leisure. Okay. So here, a pie chart, we have 100% of our time, and we're going to break it down. So we have a big circle, and we know that 40%, so almost half, so here would be 50%, so let's call 40% like that, would be studying, which is green. So we could put 40 in here, and then it would be shaded green. Okay, and then fun is going to be an additional 33%. So that might be up to here. And this is, we'd put 33, and we'd shade it red. We have an additional 20% sleeping. So we put 20 right here and shade it blue. And then our last one is black for the last 7%. and we'd shade this one black. So it's not fully shaded, but you get the concept of how we would use a pie chart. Again, we could have taken this information and made it a bar graph where we'd have 4 different colored bars. But in this case, if we want to understand our breakdown of our time, right, a pie chart might be the best way to represent this kind of information. So we have a different graph for a different purpose, right? It presents information differently, and this might best suit what we want to look at. Okay, and then the last example might be a line graph. Okay, and we'll call it a time series. So we want to track how one person, I want to track, let's see, how many, let's say, I don't know, how many hours you spend playing basketball in a week. Okay, so we're going to track 52 weeks, so we're going to track 52 observations per week, how many hours you spend playing basketball. So here's time. And this is number of weeks, so we might have week 1, week 2, all the way to week 52. We're going to record you for a year. And this is hours per week playing basketball. Okay? And it might look something like this, where over the time you commit, so your New Year's resolution was to play more basketball. So you start out kind of slow, and then you work your way up, and then summer hits, like you hit summer, and maybe it goes down, but it changes kind of like that. Okay, so we have different information, so we're tracking something over time, and a line graph is something that tracks that kind of information, or that's a very appealing graph for time series. Okay. So here we have 3 different graphs to represent 3 different kinds of information. And again, these are just one variable graphs. Okay? We have a second kind of graph, which is a 2 variable graph. So let me erase this. Okay, and a 2 variable graph is going to have 2 variables. So we're going to have a variable on the x-axis and a variable on the y-axis. And we want to understand what is the relationship between x and y. Okay, so for example, suppose that we are going to look at, let's see, what is the example that I have here? Oh, yes. So when I first moved here, the Missouri River was flooded in Omaha. And so this was in 2011 where there was heavy flooding in Omaha and it took out a bridge and so forth. So I wanted to look at the inches of rainfall, which is going to be on our x-axis. And then I wanted to know the number of floods that we had. So our y-axis is going to be the number of floods. So I'm looking at how much rainfall did an area get, and then how many floods were in that area as a result. And what we'd expect is that the more rain somewhere got, the more floods we would tend to see. So we'd tend to see a positive relationship. So a positive relationship between rainfall and floods would be represented by an upward sloping line in this graph. Okay? If we had an inverse relationship, or a negative relationship, it would be a downward sloping line. Okay? So in this case, we have a positive slope. So we have our independent variable, and we say that rainfall is going to cause flooding. So our independent variable, rainfall, which is the causing factor, goes on our x-axis. And on the y-axis is our dependent variable, or we say that x is going to cause y. Okay, so this is our 2 variable graph. Okay. The next thing that we might be concerned about is what happens if we want, or what's the expected additional number of floods for an additional inch of rainfall. Okay, so what we're thinking about is we're thinking at the margin, and we want to know if we have 18 inches of rain, and we say that 18 inches of rain would cause maybe 2 floods. What happens if we got an additional inch of rain after 18 and we go up to 19? And we want to know how much is the expected number of floods increase with an additional inch of rainfall. In this case, what we really want to know is what is the change in y for a given change in x, which is what we call the slope. So if we're thinking at the margin on a 2-variable graph, the margin is going to be the slope of our line. Okay, so in this case, let's say that we went up to 2.3. So here, we would expect 2.3 floods. So here, the change in y was 2.3 minus 2, which is 0.3, over 19 minus 18, which is 1. So the slope would be equal to 0.3, or floods per inch of water. Okay, so we're looking at the slope, and that's helping us think at the margin as well. Okay, so we're going to use slopes of our graph. The next one is what happens if we have a third variable. So we have a 2-variable graph here, rainfall and floods, but what happens if we have a third variable? So for example, let's suppose that there are no levees in Omaha right now. Okay, so in Omaha, we have this line for 0 levees. Okay, and so again, this is like, we'll call this 1, 2, 3, and 0 obviously. And then we'll have 10, 20, 30. Okay, so with 0 levees, with 10 inches of rain, we would expect 1 flood. With 20 inches of rain, we would expect 2 floods. And with 30 inches of rain, we would expect 3 floods. Okay. However, what happens if Omaha built a levee? So our third variable here is the number of levees. Okay. If we change a variable, if we change x, we just shift along our line. So we change x from 10 to 20. So note rainfall changed, which is on our graph, and we went from this point up to this point. Okay. If we're changing the number of levees, something else has to change. So for example, with 1 levee, suppose that we get 1 less flood for every 10 inches of rainfall. Okay, so in that case, at 10 inches of rainfall, we would still expect 0 floods. With 20 inches of rainfall, we would expect 2 minus 1, which is 1 flood. And with 30 inches of rainfall, we would expect 3 minus 1, which is 2 floods. So we connect those dots, and with 1 levee, this is what our relationship between rainfall and the number of floods would look like with 1 levee as compared to 0 levees. So what happened when we changed our third variable? What happened is we saw a shift in our curve. Okay? So if we're changing a variable that is on an axis, so changing one of these 2 variables on our 2-variable graph, we're going to shift along our curve from one point to the next. If we're going to change a third variable, something that isn't on our x-axis or y-axis, that's going to be represented by a shift in the curve itself. So the whole curve shifts. Okay? So we're going to be looking at what's the relationship between price and quantity and how much people want to buy at every price and quantity. And then we look at what happens if you win the lottery. What would happen to that relationship? Okay? We're going to represent winning the lottery by a change or a shift of the entire curve. Okay, so that's just one example of how we're going to use a 2-variable graph in this class. All right, last thing. we want to be careful. We want to use area of a triangle and area of a rectangle as well. So let me redraw this graph here. Let me use a different graph. We're going to look at an inverse relationship. So let's look at, let's see. Here's going to be the temperature outside in Fahrenheit and the number of layers that you wear. Okay, so when it's 0 out or it's very cold out, you're going to wear a lot of layers when you're outside. So you'd wear like a t-shirt, maybe a vest and a sweater, and then a jacket. So you'd have 4 layers or 5 layers. And then as the temperature increases and it gets really hot, you go down to no layers, or maybe like a bathing suit. Okay, so we have an inverse relationship between temperature outside and the number of layers that we wear. As temperature increases, the number of layers decreases. Okay, and that's represented by a downward sloping line. Okay, so let's suppose that we want to know, let's just say, what if the temperature is, we'll call it 40. 40 out. And we'll call this 3 layers. And this is 5 right here. Okay, so number 1, I'm going to ask you to find what is the area of this rectangle. Okay, so I want to know what is the area of this rectangle. So the area of a rectangle is going to be equal to base times your height. Okay, and in this case, our base is going to be from 0 to 40, which is 40, times our height, which is 0 to 3, which is 3. So the area of our rectangle in black is going to be 40 times 3, which is 120. For the second one, I want to know what is the area of this triangle. Okay, so for the area of a triangle, that's equal to 1/2 base times height. Okay, so here, so that's going to be equal to 1/2 times the base, which is 0 to 40, or 40, times our height, which goes from 3 to 5, or 5 minus 3, which is 2. So I have 1/2 times 40, which is 20, times 2 gives us 40. Okay, so the area of our rectangle is going to be 120. The area of our triangle is 40. And then lastly, if we want to know the combined area, we would just simply add them together. So after we find these areas separately, we could add them together to get the total area of the colored region. So that would be 120 plus 40, which is 160. Okay, so that's areas using the graph. And we're going to look at areas even more in depth. Okay, so you have an information on some of the mathematics that we're going to be using. So we're going to be focusing on slope. We're going to be focusing on areas. And then we're going to be shifting curves back and forth depending on if there's a positive relationship, negative relationship, so forth.